So this short video just sort of seeks to generalize the expression when systematic treatment is not required for the treatment of monoprotic acid systems. And so this is essentially just a rehash of what you would have done in a general chemistry course. And so the assumption is that the hydrogen ion concentration is essentially equal to that of the counter ion in this case, and that comes from this HA, whatever our monoprotic acid is, dissociating into H plus and A minus. And so those two things are equal to each other, meaning we're not considering any contribution to H plus aside from that of the HA minus. So the HA minus is strong enough that we don't have to consider that. So I talked quite a bit in the previous videos about when those assumptions are valid. So when those assumptions are valid, then the sort of generic relationship here that we'll establish is that via an ICE table, we'll have some formal concentration of this stuff to begin with, 0 for these two things, and some amount X of the original acid is going to dissolve or dissociate, and that's going to be produce 1X of each of those terms. So we'll have F minus X, 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 and so if we establish this into a generic equilibrium expression, that'll be Ka is equal to X times X over F minus X, which is X squared over F minus X. When we have really, really small Kas, then systematic treatment is going to be merited, but when we don't, then this general or generic formalism is reasonable. This is exactly what you would have done in a Chem 108 course. So we can do an analogous setup for weak bases. So the weak base here, typically these are bases where they've got this lone pair of electrons. Sometimes I write that up, sometimes I don't. I like to just keep that in mind. In which case it's going to lash onto one of these hydrogen protons on water, and that's going to yield this adduct of BH plus, and then the leftover bit of water, which would be hydroxide ion. And the equilibrium constant for this reaction is going to be Kb, Kb being equal to the concentration of BH plus times hydroxide ion concentration divided by the concentration of the original base in solution. So we make a really analogous assumption for weak bases. In this case, we're talking about OH minus. And so we think that the OH minus is all coming from the base and not coming from the dissociation of water. So very, very similar to what we did with the weak acid, where we said that the proton concentration is simply coming from the acid and not coming from water. Same thing is true here, hydroxide coming from base and not from the dissociation of water. If we do it that way, then that gives us this approximation where these two things are equivalent to each other, so we set those both as X. So we get X times X over formal concentration minus X is equal to Kb in this case. So same exact expression, except that is set to the equilibrium constant for the base association, or Kb. Okay, so a couple of reminders here from sort of Chem 108 days is that this expression here is the equilibrium of this expression is dictated by Kb. So remember that this is for this forward-going direction for base plus water. That's Kb. If we flip this reaction around, that is not the same as Ka. Right? Because in that case, if we reverse this reaction and we run it this way, and we want to think about what is the equilibrium constant for the protonated version of the base plus pure hydroxide, which is strong base, proceeds to make water plus base. This is not simply the Ka. Even though this is an acid, it's now reacting with a strong base instead of water. And so that would be 1 over Kb, which would be a much larger number because Kb is weak. So 1 over that value is a large number, which now essentially becomes a neutralization reaction, which we often write as Kn in a Chem 108 course. So if you want to get to the Ka from the Kb, remember that the relationship is Ka times Kb is equal to 10 to the minus 14, right? what else would I say? So if you wanted to think about, well, what is the difference between Ka and 1 over Kb here? Well, the Ka for BH plus would be BH plus water makes H3O plus base, which would also be the same thing as just simply BH plus proceeds to dissociate as H plus B. This would be Ka, which is different than what we had in this reaction, because here the protonated version of the base is reacting with pure water. In this case, the protonated version of the base is reacting with pure hydroxide. So those are two different things, right? If you're going to take a weak acid and react that with a strong base, that's going to give you a very large equilibrium constant. It's going to want to move to the right significantly. But if you have a weak base reacting with water, then that's a much smaller equilibrium, and it's going to lie further to the left, which is Ka. So be careful when you are relating acids and bases, Kas and Kbs, especially as we work a little bit more with bases in this class. You can't simply flip the reaction around and do 1 over. That's going to be that's not the same as a Ka.